Hello everyone. The topic I am going to talk it's about refrigeration systems from the topic refrigeration and cold chain management. The topic is about simple vapor compression refrigeration system. Vapor compression refrigeration cycle. In this diagram, this is the most common refrigeration cycle we use today. In this diagram, you can see a condenser. It consists of four components: condenser, compressor, evaporator, and an expansion device. In this, as you can see, the heat goes in through the evaporator and it goes out through the condenser. Uh, there are totally four principles involving these components. One is evaporator, compressor, condenser, expansion valve. In this, all energy transfers are done by work and heat are taken as positive in the direction of the arrows of the schematic and energy balances are written accordingly. These are the process. The process starts from 4 to 1, where it is a two-phase liquid vapor mixture of the refrigerant. It is evaporated through heat transfer from the refrigerator space. In process 1 2, the vapor refrigerant is compressed to a relatively high temperature and pressure requiring work input. In the process 2 to 3, vapor refrigerant it condenses to liquid through heat transfer to the cooler surroundings. And finally, in the process 3 and 4, liquid refrigerant it expands to the evaporator pressure. Then about vapor compression refrigeration cycles engineering model. Each component is analyzed as a control volume at steady state. In this, the dry compression it is presumed the refrigerant is a vapor. The compressor it operates adiabatically. The refrigerant expands through the valve undergoing a throttling process. In this, the kinetic and potential energy it changes are ignored. Then by applying the mass and energy rate balances for evaporator, Q in by M is equal to H1 minus H4. In this, the term Q in it is heat which is referred as the refrigeration capacity and it is expressed in kilowatt in the SI unit system. A common alternate for the unit is ton of refrigeration which is equal to 211 kilojoules per minute. Then about compressor. By applying mass and energy rate balances to the compressor, we can assume that the adiabatic compression which is WC by M is equal to H2 minus H1. Then in condenser, it is Q out by M which is H2 minus H3. And for expansion valve, assuming it's a throttling process, it is H3 is equal to H4. Then performance parameters. In this COP, which is coefficient of performance is Q in by M by WC by M, which is H1 minus H4 by H2 minus H1, which is equal to TC, which is TC by TH minus TC. TC is cooling temperature and TH is heating temperature. These are the coefficient of performances. First one is about coefficient of performance of refrigeration machine and second is the Carnot coefficient of performance. In this equation it represents the maximum theoretical COP of any refrigeration cycle operating between cold and hot regions at TC and TH respectively. Then features of actual vapor compression cycle. In this the heat transfers is between refrigerant and cold and warm regions which are not reversible. As you can see in the diagram, the cold region which is shown at the down of the slope which is the temperature of cold region and the hot region is shown at the top of the slope which is the temperature of hot region. In this the refrigerant temperature in evaporator is less than Tc. The refrigerant temperature in condenser it is greater than Th which is a hot temperature. In this the irreversible heat transfers it has a negative effect on the performances. Then features of the actual vapor compression cycle. In this the COP decreases because it is primarily due to increasing in the compressor work input, as the temperature of the refrigerant passing through the evaporator is reduced which is relative to the cold temperature Tc. As you can see the temperature is getting reduced. The temperature of the refrigerant passing through the condenser is increased relative to the temperature of the warm region Th. Then features of actual vapor compression cycle. This irreversibilities during the compression process are suggested by dash line from state 1 to state 2. An increase in specific entropy accompanies an adiabatic irreversible compression process. The work input for compression process 1 2 it is greater than for the counterpart isentropic compression process 1 to 2s. Since process 4 1 and thus the refrigeration capacity is same for cycles 1 2 3 4 to 1 and 1 2 is 3 4 to 1. Cycle 1 2 3 4 to 1 it has lower COP. Next, isentropic compressor efficiency. In this, it is the ratio of the minimum theoretical work input to the actual work input each per unit of mass flowing. In this, the isentropic compression efficiency NC is equal to minus WCV by MS by minus WCV by M, which is equal to H2S by H1 by H2 minus H1, which is the actual compression by isentropic compression. This the work required is an isentropic compression from compressor inlet state to the exit pressure. Down it shows the work required in an actual compression from compressor inlet state to exit pressure. Then the pH diagram. The pressure enthalpy pH diagram is a thermodynamic property diagram which is commonly used in the refrigerator field. In this, it shows the process of 2, 2s, 3 and 4, which shows the evaporator and condenser are opposite to each other. The pressures of evaporator and condensers are opposite each other. That's what it says. Thank you.